Hi class, Mr. Morris again. Last class we talked about rate law. This class we're actually talking about kind of an adaptation of that. We call it concentration changes over time. That's the new AP chemistry title for it. Traditionally it's called integrated rate law. Well, let's recall from last class what we talked about. In rate laws, unit 5.2, we saw the relationship between the rate of the chemical reaction, and the concentration. And typically the concentration, as the concentration increases, the rate also increases, with the exception being a zero order reaction. Today we're going to talk about a different type of rate law. We call it the integrated rate law. So to analyze the relationship between concentration and time, we will need to integrate the rate law, where integrate is a calculus term, and I can explain in more detail what that is outside of class, for those of you who would like to know, especially if you're in calculus, you maybe already kind of understand what we mean by integrating the equation to find the rate law. But if not, you don't really need to know calculus in order to do this. We'll go through everything you need to know in this video and in the videos to come. So let's kind of summarize a combination of what we learned last time and the main points of this one. This kind of summarizes it. The first three columns in this image are from the last set of notes. We have our order, 0, first and second order, the rate law, which is k times a to the 0, or just k for 0 order, and then the rate equals k times a to the 1, or just k times the concentration of a for first order. And for second order, it's k times the concentration of a squared, or whatever the reactant is, of course. It could be plugged in for the place of a. We've got our units of K, and although you probably don't have those memorized, I hope you could figure them out when you plug in the units into our rate law expression. But today we're going to talk about the integrated rate law. Now, you do not need to memorize these integrated rate laws. On the equation sheet, you're going to have this section from kinetics, and these are the rate laws. I want you to know the order of them and be able to quickly find it, because you'll need to refer to this section in the equation sheet during the test. You need to know that this first one corresponds to 0 order. The second one is first order, and the third one is second order. Okay, so it will not be labeled. You just need to know that 0, first, second. That's the order it goes in. 0 order, first order, second order. Then this half-life down here, we'll talk about what that is, but T1/2 is the half-life equation. This is for a first order reaction, and that's the only one you'll need to know the the equation for, unless it's given in the problem. So the half-life of a first order reaction is also included on the equation sheet. So back to these rate laws, these integrated rate laws. You notice that these are written in a little bit of a different form, but if you rearranged, they're actually exactly the same as this down here. What you are going to be evaluating is the graphs more than anything, the graphs. And when you have a straight line on the plot of concentration versus time, that's a 0 order reaction. When the straight line graph is on Ln of concentration versus time, that's a first order reaction. And when the straight or linear slope is a graph of 1 over concentration versus time, where your y-axis is 1 over concentration, or maybe inverse concentration, a to the negative 1, and the x-axis is time, that is second order. And to keep that straight, we can look back at our rate laws. Concentration and time, 0 order. Ln of concentration and time, that's first order. And second order is the last one, 1 over concentration, inverse concentration versus time. So you do have this as an aid to help you to answer those questions. You don't have to memorize it. You just need to know how to understand it. But what about this talk of having a linear or nonlinear graph? Let me just give you an example really quickly. Now, there's an AP Daily video you're going to watch that goes through these example problems, but I just want to give you an idea. You see that of these three graphs, there's only one that's a straight line. We've got a downward sloping curve here. We've got an upward sloping curve here. The downward sloping line is this graph. And it says on the y-axis Ln of absorbance. And remember that absorbance is directly proportional to concentration. So that's going to correspond to the rate law, which the integrated rate law, where Ln of concentration is proportional to time. So Ln of concentration is proportional to time on our equation sheet. That's the second one. It's our first order reaction. So we would know this, going back to that example, this is first order because the only one that is straight is Ln of absorbance. That's a preview of what you're going to be learning from the upcoming video in the next few minutes. I want to give you some just important notes for integrated rate laws. And I'm sorry, back up just a little bit. This is just information about what is included in the equations and in the graphs. T is the time elapsed since the beginning of the observation. It's going to be in units of seconds, minutes, hours, or some other unit of time, maybe even a day. Concentration of A sub 0, and then we've got concentration of A sub T. Well, A sub 0, that's the concentration at the beginning of the observation before any time has elapsed. And then A sub T is the time at is the concentration at a specific time, where that's T. Half-life, T1 half. This is important. T1 half, that's the time required for the concentration of the reactant to fall to 1/2 of its initial value. It's the time it takes for the concentration to be half of the original concentration. So some important notes when you're solving problems, when you're watching these videos and trying the practice problems, and then when you do the practice, which is practice FRQs from previous AP exams. First thing we need to note, when you're given a set of data or graphs, how can you tell the order of the reaction? We're going to find the Ln and the 1/A values. If they're not already calculated, plot them if they're not already calculated or not already plotted for you, and you're going to have 3 total graphs. Find the graph that's linear. If it's concentration of A on the y-axis, that's going to be 0 order. If the y-axis is Ln of A, where T is the x-axis, it's first order. But if it's 1 over concentration of A, where T is the x-axis, and that is the one that is linear or straight line, that'll be second order. All right, how do we determine the K value? Well, with an integrated rate law, the K value is the slope. The slope of the linear plot is the K value. And you can use the units for the axis to determine the units of K. Remember, to find the slope, it's rise over run. It's whatever the y-axis units are divided by the units of the x-axis. And you've got to know that Ln of A has no units. So the Ln, the y-axis has no units. It would just be 1 and then divided by the units of the x-axis, time. For 0 order and first order, the slope of the linear line is going to be negative. Make sure that you have a positive number for your K value. So just know that the K values will always, always, always be positive. If not, make it positive. Just change it into a positive number. So 0 in first order, you'll have to do that. How do you determine the concentration at a given time? If it's outside the range of the graph or data table, you'll need to use this. It may not make a lot of sense right now, but this note number 3, note this. You're going to have to come back to it when you're answering the questions in the practice problems. I think the first one, at least, you have to do this. The first practice problem today, you have to follow these steps. How do you determine the concentration at a time that's not given in your data? so you can't just look at a plot and pick it. Well, we're going to use the integrated rate law. Again, one of these, we're going to figure out which one it is. Is it 0, first, or second order? And then once you know that, you're going to use that rate law, and we're going to plug some numbers in. And we're going to use the data from t equals 0 and the k value that's probably solved for in an earlier step. Those are all values we can plug into the rate law equation. The only thing that's left unknown is going to be the concentration of A at the time that is asked for in the problem. Plug in the time. Then you will rearrange and solve for the concentration at that given time. Remember, to undo an operation, to switch sides and solve, we're going to do the opposite operation, or the reciprocal operation. The reciprocal operation of ln is e. So ln of x, it's that lowercase e to the x. It's called Euler's number on your calculator. All right, and then finally, half-life behavior. This is discussed in the second AP Daily video that you'll watch today. We're going to only use, only the half-life of first-order reactions is actually constant. And we've got the equation given on the equation sheet. Don't worry about memorizing it. It will be given to you. Checking to see if the half-life is constant is often the best way to confirm that a reaction is first order. So if it asks to confirm that a reaction is first order, if you have a graph or a data table, check the half-life and see, compare the first half-life and the second half-life. If it's the same amount of time, it's a constant half-life that makes it first order. Using the equation above, so this equation right here, it's often the best way to find K for a first order reaction. So if it is a first order reaction, it's easy to know the half-life, and then we just do 0.693 divided by the half-life. That'll give you K. And then don't worry too much about these two facts. It's just information in the notes for you to be aware of. The half-life of a zero-order reaction, it decreases with time, and the half-order for a second-order reaction increases with time. We've got their general equations right here. When a given concentration versus time graph, determine the first half-life and then determine the second half-life. By comparing the half-life value, the order of the reaction can be determined. It's basically what we just talked about up here. I want you to note that all radioactive decay processes have first-order kinetics, and they have a constant half-life as a result. That's really all of the preview, the notes that I wanted to go over with you guys. Now watch the AP Daily video 1. It gives you some good information and practice problems to work through. You've got one that talks about half-life when you get down here to the second AP Daily video. Those are both pretty short. Answer the questions, and then I'll insert another video right at the end to talk about integrated rate law determination when you've got more than one reactant.